Welcome to our deep dive into multithreading in Java. In today's fast-paced digital world, applications need to be responsive and efficient. That's where multithreading comes in. By allowing multiple threads to run concurrently, Java enables programs to make the most of modern CPUs. Whether you're building desktop software or high-performance servers, understanding multithreading is essential. In this video, we'll explore the core concepts, practical examples, and best practices for writing robust multithreaded Java applications. Let's start by understanding the basic building blocks: CPU, cores, programs, processes, and threads. CPU, often called the brain of your computer, is responsible for executing instructions from programs. It performs arithmetic, logic, control, and input-output operations. Modern CPUs are designed with multiple cores, each capable of handling its own tasks. This means your computer can do several things at once, like playing music while you browse the web. Understanding how the CPU and its cores work is crucial for leveraging multithreading in Java. As we move forward, keep in mind that efficient use of the CPU is at the heart of high-performance applications. Core is an individual processing unit within a CPU. Think of it as a mini CPU inside the main chip. Modern processors can have multiple cores, dual-core, quad-core, or even more. Each core can execute its own thread independently, allowing true parallelism. For example, a quad-core processor can handle 4 tasks at the same time, like running your browser, music player, download manager, and a system update all at once. This parallelism is what makes multithreading so powerful in Java applications. Program is simply a set of instructions written in a programming language, telling the computer how to perform a specific task. When you run a program, the operating system creates a process to manage its execution. For instance, when you open Microsoft Word, it becomes a process in your operating system. Each process has its own memory space and resources, ensuring that programs run independently and securely. This separation is key to understanding how threads operate within processes. Thread is the smallest unit of execution within a process. While a process can have multiple threads, each thread shares the same resources but can run independently. For example, a web browser like Chrome might use separate threads for each tab, allowing you to browse multiple sites without one tab freezing the others. Threads make applications more responsive and efficient, especially when performing tasks like downloading files or rendering graphics. Multitasking allows an operating system to run multiple processes at the same time. On single-core CPUs, this is achieved through time sharing, where the CPU rapidly switches between tasks to create the illusion of simultaneous execution. On multi-core CPUs, true parallel execution is possible, with tasks distributed across different cores. The operating system scheduler manages this balancing act, ensuring efficient and responsive system performance. Multithreading refers to the ability to execute multiple threads within a single process at the same time. For example, a web browser can use multithreading by having separate threads for rendering pages, running JavaScript, and handling user input. This makes the browser more responsive and efficient. By breaking down tasks into smaller threads, multithreading maximizes CPU usage and improves application performance. Time slicing is a technique where the CPU divides its time into small intervals, called time slices or quanta. The operating system scheduler allocates these slices to different processes and threads, ensuring each gets a fair share of CPU time. This prevents any single process or thread from monopolizing the CPU, which is especially important on single-core systems. Time slicing is fundamental to achieving multitasking and multithreading. Context switching is the process of saving the state of a currently running process or thread and loading the state of the next one to be executed. When a thread's time slice expires, the OS scheduler performs a context switch, moving the CPU's focus to another thread. This mechanism allows multiple threads to share the CPU, creating the appearance of simultaneous execution even on single-core systems. Java provides robust support for multithreading, making it easy for developers to create applications that perform multiple tasks simultaneously. Java's multithreading capabilities are built into the Java Lang package, allowing for concurrent execution of threads. Whether you're working in a single-core or multi-core environment, Java's threading model adapts to maximize CPU utilization and application responsiveness. In a single-core environment, Java's multithreading is managed by the JVM and the operating system, which switch between threads to give the illusion of concurrency. Threads share the single core and time slicing is used to manage execution. In a multi-core environment, Java can distribute threads across multiple cores, allowing true parallel execution and significantly boosting performance. In Java, you can create threads in 2 main ways: by extending the thread class or by implementing the runnable interface. Extending thread is straightforward but limits inheritance, while implementing runnable allows your class to extend other classes. Both approaches require you to override the run method, which contains the code to be executed by the thread. When you extend the thread class, you create a new class that inherits from thread and override its run method. To start the thread, you call the start method, which internally calls run. This approach is simple and direct, but remember, Java only supports single inheritance, so you can't extend another class if you already extend thread. Alternatively, you can implement the runnable interface. This method is more flexible as it allows your class to extend other classes. You override the run method and pass an instance of your class to a new thread object. Then, you start the thread by calling start on the thread instance. This approach is widely used in real-world Java applications. Thread in Java goes through several states during its lifecycle: new, runnable, running, blocked, waiting, and terminated. When a thread is created, it's in the new state. After calling start, it becomes runnable, waiting for CPU time. When executing, it's running. If waiting for a resource, it's blocked or waiting. Once finished, it's terminated. Understanding these states helps you manage thread behavior and debug. Choosing between runnable and thread depends on your needs. Use runnable when you want to separate the task from the thread, allowing your class to extend another class if needed. Extend thread if you need to override thread-specific methods or require direct control over the thread. Generally, implementing runnable is more flexible and preferred in most cases. Java's thread class provides several important methods. Start begins execution, run contains the thread's code, sleep pauses execution, join waits for a thread to finish, set priority changes thread priority, interrupt signals a thread to stop, yield hints the scheduler to switch threads, and set daemon marks a thread as a background or user thread. Mastering these methods is essential for effective multi-threaded programming. Threads in Java can have different priorities ranging from thread, min priority 1 to thread max priority 10. The scheduler uses these priorities as hints to decide which thread to run next. However, thread priorities are not guaranteed to be strictly enforced, as actual behavior depends on the JVM and operating system. Use priorities to suggest importance, but don't rely on them for critical logic. Daemon threads are background threads that support user threads. When all user threads finish, the JVM exits, terminating any remaining daemon threads. Common examples include garbage collection threads. You can mark a thread as daemon by calling set daemon true before starting it. Daemon threads are useful for background tasks that shouldn't prevent your application from shutting down. When multiple threads access shared resources, synchronization is crucial to prevent data corruption. Without synchronization, threads can interfere with each other, leading to unpredictable results. For example, two threads incrementing the same counter may not always produce the expected result. Java provides the synchronized keyword to ensure that only one thread can access a resource at a time. Race condition occurs when two or more threads access shared data at the same time, and the result depends on the order of execution. Without proper synchronization, this can lead to inconsistent or incorrect results. For example, incrementing a shared counter without synchronization may cause some increments to be lost. Always protect shared resources to avoid race conditions. In Java, you can synchronize methods to ensure that only one thread can execute them at a time. By adding the synchronized keyword to a method, you prevent other threads from entering the method until the current thread finishes. This is a simple way to protect shared resources, but it can impact performance if overused. While the synchronized keyword provides basic thread safety, Java's lock interface offers more advanced control. Locks allow you to acquire and release access to resources explicitly, support tri-lock mechanisms to avoid indefinite blocking, and enable multiple condition variables for complex coordination. The reentrant lock class is a common implementation, providing flexibility and power for advanced concurrency scenarios. Reentrant lock allows a thread to acquire the same lock multiple times without causing a deadlock. This is useful when a thread needs to enter synchronized blocks or methods repeatedly within the same execution flow. The reentrant lock class provides features like tri-locking, timed locking, and multiple condition variables, making it more flexible than the synchronized keyword. Reentrant lock provides several important methods. Lock acquires the lock, blocking if necessary. Tri-lock attempts to acquire the lock without waiting. Tri-lock with timeout waits for a specified time. Unlock releases the lock, and lock interruptibly allows interruption while waiting. Always release locks in a finally block to avoid deadlocks. Read-write locks allow multiple threads to read shared data simultaneously, but only one thread can write at a time. This improves performance in scenarios with frequent reads and infrequent writes. The reentrant read-write lock class provides read and write locks, optimizing access to shared resources while preventing data inconsistency. Fairness in locking ensures that threads acquire locks in the order they requested them, preventing thread starvation. A fair lock grants access to the longest waiting thread next. While fairness prevents starvation, it can reduce throughput due to the overhead of maintaining order. Non-fair locks may offer better performance but risk some threads waiting indefinitely. Deadlock occurs when two or more threads are blocked forever, each waiting for the other to release a resource. This typically happens when threads hold locks and request additional locks held by others. For example, thread A holds lock 1 and waits for lock 2, while thread B holds lock 2 and waits for lock 1. Neither can proceed, causing a deadlock. Avoiding deadlocks requires careful design and resource management. Threads often need to communicate and coordinate their actions. Java provides wait, notify, and notify all methods for thread communication. For example, a producer thread can notify a consumer thread when data is available. Proper use of these methods ensures smooth cooperation between threads and prevents issues like missed signals or lost updates. Executors framework, introduced in Java 5, simplifies concurrent programming by abstracting thread creation and management. It provides thread pools, resource management, scalability, thread reuse, and error handling. By using executor service, you can submit tasks for execution without worrying about manual thread management, making your code cleaner and more efficient. With executor service, you can submit tasks for execution using methods like submit and execute. The framework manages a pool of threads, reusing them for new tasks and efficiently handling resource allocation. After submitting tasks, you can shut down the executor to release resources. This approach is ideal for scalable, high-performance applications. Future interface represents the result of an asynchronous computation. When you submit a task to an executor service, it returns a future object. You can use future.get to retrieve the result, which blocks until the computation is complete. Future also provides methods like isDone to check if the task is finished. This makes it easy to manage and coordinate asynchronous tasks. Java provides atomic classes like atomic integer for thread-safe operations on single variables without explicit synchronization. These classes use low-level atomic instructions to ensure that operations like incrementing a counter are performed safely, even when accessed by multiple threads. Atomic classes are ideal for simple thread-safe counters and flags. Volatile keyword in Java ensures that changes to a variable are immediately visible to all threads. It prevents threads from caching variables locally, guaranteeing that they always read the most up-to-date value. Volatile is useful for simple flags and state variables, but it doesn't provide atomicity for compound actions like incrementing a counter. Countdown latch is a synchronization aid that allows one or more threads to wait until a set of operations being performed by other threads completes. You initialize it with a count, and each thread calls countdown when it finishes. The waiting thread calls await, blocking until the count reaches 0. This is useful for coordinating tasks like waiting for multiple services to start. Cyclic barrier is another synchronization aid that allows a set of threads to all wait for each other to reach a common barrier point. Once all threads reach the barrier, they can proceed together. This is useful for scenarios where multiple subsystems must be initialized before the system can start. The barrier can be reused, making it suitable for iterative tasks. Classic example of thread communication is the producer-consumer problem. One thread produces data and notifies the consumer thread when data is available. The consumer waits for the producer to produce data before consuming it. Using wait and notify, you can coordinate the actions of both threads, ensuring smooth data flow and preventing race conditions. Exception handling is crucial in multi-threaded applications. Uncaught exceptions in threads can cause them to terminate unexpectedly. Java allows you to set an uncaught exception handler to handle such cases gracefully. Always use try-catch blocks in your thread code to manage errors and ensure resources are released properly. Thread pools are a key feature of the executors framework. They manage a group of reusable threads, reducing the overhead of creating and destroying threads for each task. Thread pools improve performance, resource management, and scalability, making them ideal for server applications and high-load systems. To write robust multi-threaded applications, follow best practices. Minimize shared state, use thread-safe collections, prefer higher-level concurrency utilities over low-level synchronization, avoid deadlocks by acquiring locks in a consistent order, and always release resources in finally blocks. Testing and profiling are essential to identify and fix concurrency issues. Debugging multi-threaded applications can be challenging due to timing issues and race conditions. Use logging, thread dumps, and specialized tools to trace thread activity. Pay attention to thread states and synchronization points. Consistent and thorough testing helps catch subtle bugs that may not appear in single-threaded scenarios. Common pitfalls in multi-threaded programming include forgetting to synchronize shared resources, causing race conditions, holding locks for too long, leading to performance bottlenecks, and improper exception handling, which can terminate threads unexpectedly. Always review your code for these issues and use Java's concurrency utilities to simplify development. Multithreading is ideal for tasks that can be performed independently, such as handling multiple client requests, processing large datasets, or performing background computations. However, it adds complexity and should be used judiciously. For simple tasks, single-threaded solutions may be more maintainable and less error-prone. Summary: multithreading in Java unlocks the full potential of modern CPUs, enabling responsive and high-performance applications. By understanding threads, synchronization, locks, and concurrency utilities, you can write robust and efficient code. Remember to follow best practices, test thoroughly, and use the right tools for the job. With these skills, you're ready to tackle complex, real-world Java projects. Now that you have a solid foundation in Java multithreading, continue exploring advanced topics like concurrent collections, thread pools, and parallel streams. Practice by building sample applications and experimenting with different concurrency patterns. The more you code, the more confident you'll become in writing scalable, high-performance Java software.